This week's topic is logic, and thinking about kind of the relationship between of proving stuff and the business of programming, with hopefully not too ideological a perspective, but to just try to be pragmatic about well, how we might make use of interesting types to tell more truth, although this lecture appears to be about not so interesting types. We shall see. But yeah, I mean, it's also one of those things where, although with your particular year group, I feel slightly less bad about it because I didn't do the damage. But round about this time of year, someone teaching first year classes it's introducing logic in terms of truth values that are 0 and 1 and all of this truth table business. And sure, we can play games which involve having a data type of Booleans containing 2 values, which we call false and true, and we can define familiar looking logical connectives. So let's, no panic. So yes, if we could define conjunction as a thing, as a Boolean operator. So the one way to do it is this way.
We pattern match on the first argument. We can actually get our logical connectives just as operations on Booleans. But is that good enough actually?
Yeah. Well, so the thing we can use this, we can use this to compute whether finitely many tests come out true. So if we're in the business, I mean, yeah, so, you know, if we're building up a Boolean expression with conjunction, it's going to be only finitely large, so it can make only finitely many demands. So for example, if we wanted to express the property that, I don't know, adding 0 to every number, well, you know, to a given number leaves it unchanged, right? If we want to, for all x plus 0 equals x, then sure, you know, we can test that for, you know, 2, 5, 37, you know, 642. But we can't write down a big conjunction that says, you know, all the tests that have to pass. So we might want some different way to represent that statement and some different way to argue in favor of that statement. So I think I usually do say to the first year, using kind of a Boolean type as a way of doing, as a way of managing logic is absolutely fine. Indeed, the right thing to do sometimes when you're in a situation where you're only interested in testable stuff. But if you're interested in arguing about infinitary things, it's maybe not so helpful. That kind of thing, but also the fact that if you lick your finger and press the piece of metal, you can find out whether you get electrocuted or not. You know, what was the thing here is that it's always good to learn how to interrogate a type, right? So the two questions you should always ask about a type are, how do I make one of you? And what good, if somebody gives me one of you, what good is that to me? So here we declared the Booleans to have two values, false and true. So that's the answer to, how do I make a Boolean? You either deliver false or you deliver true. That's to say, you provide a bit. And then, you know, what good does it do me to know a bit? Well, I can look at it to see which one of those two things it is, and it better be one of them, right? Computational deal is that there are no secret magical bits, that everything that promises you a bit is actually going to come off the fence and deliver false or deliver true. That's quite a powerful promise, right? I mean, so things might take a while to deliver that bit, but they're not going to take forever. And there are no kind of, there's no magic, and the absence of magic is going to show up in some important ways. So yeah, so the idea here is that we're going to work with notions of evidence. So you can think of right. It's kind of, well, usually when we talk about evidence in conversation, we either say evidence for something or evidence that's something, or there's some background context that makes it clear what the evidence is about, you know, what's at stake. But the evidence is consisting of some sort of data, but it's data with a known purpose. It's not just like, I've got a bunch of bits, you know, 3 of them are 0 and 5 of them are 1s. It's, you know, what's it for? It's data with intent. And we got types that are good at describing acceptable forms of data. So the idea here is to try and capture notions of logical statement as types that characterize the evidence that would be adequate for demonstrating the logical statement. Start with conjunction. I guess you can stay put for conjunction, and I'll do the next one.
Okay, so what would be the evidence of a statement that says A and B? So think of it as in a type theoretic way. So what types, if we have the evidence for A and the evidence of B, how can we combine them in a single type that describes the proof or evidence of A and B? And a way to do that is actually to take their product, or just to have something that combines them together at the same time. And we can see that this is imported from the standard library, so we can check its definition. And
Yes, so we're reconstructing the connectives. You know, if we have an idea of what would be evidence for A on its own, what would be evidence for B on its own, then now let's think, how would we represent evidence for the statement A and B? Where A and B are arbitrary.
And that evidence is defined as a record here that has multiple fields. And the first one will hold our evidence for A, and the second one will hold our evidence of B. And this is the definition that in the standards, however, and we can see that we can construct that evidence with the constructor comma.
Yeah, so this is actually a more general construction, which we will come back to. But in that's a dependent version. But if we're in a simple case where A and B are kind of independent concepts, then we're just talking about same sort of notions of pairing that you get in Haskell. Yes. Yeah, well, so the comma will show up, right? So this type A cross B, I'm taking that is defined. How is it defined? Yes, it is defined to be a degenerate dependent pair. That's to say, so yeah, I kind of would like to talk about
I think we'll get back to
we'll get back to it. But yeah, so basically there's a sort of general notion of records where later types of fields in the record can depend on earlier values. And a pair, an ordinary pair, is a record with two components that does not use this superpower to allow other, you know, the types of other components to depend on values. But the constructor is the same thing. So we're still building pairs with comma. It's just that there happens to be no dependency between the components. So
okay,
yeah.
So going back to our conjunction, let's actually define our conjunction. So now if we have our notion of propositions, that is a bunch of evidence supporting that, how we are going to say what is a conjunction of A and B, and as we saw, this is a non-dependent product. So we demand two pieces of evidence, one supporting A and one supporting B.
Yeah, so let's be systematic, right? Same game. How do I prove you? What use is it if someone gives me a proof of you? So how do we prove A and B? We prove A, we prove B, we collect the two proofs in a pair. And what good is it to know A and B? Well, turns out if you've got a pair of proofs, you can unpack them.
So we can introduce the proof of A and B, and then we can pattern match on it.
And it chooses stupid names. Just
So
rather they were called little A and little B.
And now we can see that by pattern matching, we obtained a proof of A, a single proof of A and a proof of B. So now we can just give our proof of A. Another way to do that would be to directly use the rejection functions that come from the library instead. And these are very suggestively called proch1 and proch2.
Are they called? Okay, yeah, you need to look that up to see why that is. Yeah. I thought they were first and second, but maybe I'm confused.
And we can project out the first part of the proof of A and B, namely the proof of A. Now, so we saw how to use a proof of a conjunction, but how can we produce a proof of a conjunction? And in a simple case, how can we produce an evidence supporting A and A? And here we can.
Sorry, headsides one now. If you write this as prod one, is that not just saying we have defined this in terms of this thing that we're defining as that we're just renaming prod one?
Yeah, that's all that's going on there.
Yeah, we can even take it a step further and
I'll just say X1 equals prod one.
yes.
Yes, the pattern matching definition is clearer, but up to a
So
point.
it's prod one definition exactly that matching definition.
No, well, so it's not actually.
Oh, it's
Let's look at the definition. I suspect it's defined to be because the actual, so somewhere proj. What's troubling me is that, yeah, when we visited this definition, the components were called fust and sund. So where did the proj come from? That's what's.
I think it was an independent type definition.
I think we're. Right, in the thing that defined non-dependent product into dependent product. Oh, there's a renaming when the import happens.
Yes.
First is renamed proj 1 and sund is renamed proj 2. So that makes some sense. There is a sort of I think, was that our first record?
I think so, yes.
Yeah. So Agda, unlike Haskell, distinguishes records from data types. And the idea is that to give a data type, you say all the ways of building the data. To give a record type, you say all the ways of using the data. So you specify all of the projections. The distinction is data asks, what can you put in? Records ask, what can you get out? And then to build a record, you have to be able to answer all the how do you get this out questions. You have to define all of the projections, all of the components. Whereas to make use of a data type, you have to give a case for each of the different ways of building the data. So in some sense, records are a big generalization of and, whereas data are a big generalization of or.
For any record, you construct data.
Yes.
Over this.
There are, yeah, so you could give a data type which had one constructor that happened to take two parameters, and then you could do pattern matching to extract those parameters. And there are reasons why we prefer not to do that, and we will get there. What's happening is that we get, we're trying to do something really simple, and in order to explain where what's going on in all of these definitions, we have to step on a whole bunch of landmines too early.
But
yes.
Let's maybe go back to doing something very simple.
Yes.
So now, how do we produce a proof of that conjunction A and A, where we are given a proof of A? And now we have to produce our tuple here. indeed. And if we're feeling especially lazy, we can refine that. So Agda knows that this type has one constructor and just introduces the constructor for us. And then we can indeed say A and A.
Yes, so that keystroke was Control-C, Control-R, R for refine. And refine means if there's exactly one constructor that can go here, put it there. So there's only one way to build a record, and that's to give both pieces, to give all the pieces to prove a pairing. Give both. In this case, we're just going to duplicate the proof of A that we already have.
Okay, so one logical connected down, a few more to go.
Yeah.
And now we get to a bit more interesting one, which is implication.
Okay. Do you want to keep driving about
Yes.
the topic? Cyrillic keyboard. Right, got no chance. Right. Okay. So here's the thing. What would be convincing evidence? If we know what evidence for A consists of, and we know what evidence for B consists of, what do we think evidence for A implies B might consist of?
Go ahead.
Function from A to B, yeah. So that's to say, you would, there are circumstances under which, if you claim A implies B, there are circumstances, if you claim to be able to prove that A implies B, there are situations in which you could be called upon to produce evidence for B. Namely, if someone turns up at your shop with evidence for A. Okay, here's your proof of A, what are you going to do about it? So we just directly use the function space of our underlying programming language as a way of saying proofs of implication are ways of translating evidence for one thing to evidence for another. So, for example, we hope that that A implies A always holds, right? If we have evidence, if we're given evidence for A, we should be able to give back evidence for A by means of one of our favorite functions, namely, well, we can introduce a name for the proof that we're given, and then it's clear that we have something we can directly give back. So the good old identity function is it's going to help us out here. But sometimes it's a bit more of a tricky business. So here we've got this big implication. So we can give that a name. Let's just do one thing at a time and keep looking. At the moment, we're being asked to prove this big, complicated implication, but just work a little bit at a time. So let's introduce F on the left and see what we've got. Okay, so we've got an F here. It makes D's given some stuff. Okay, and we can, now we're trying to prove another implication. So we can give this thing a name. Okay. And now you can see we've got our F and our G, and now we're being asked for a proof of D. Can you see any way to get your hands on a proof of D? I should not lean against that. Yeah, we need to call F and hope we can think of something. So, I mean, it's F or bust, right? The only thing that's talking about D is F. So it must be F applied to something, who knows what. Okay. We've got, now we're being asked for a proof of A implies B implies C. So just to check, arrow groups to the right. So this is, if we were putting parentheses to disambiguate this, they go around B implies C. And that's a sensible thing to do, given the way we pretend functions have multiple arguments. Yep. So actually, this is a job where refine isn't a crazy thing to do.
Yes.
And then it decides to give us an A and a B, both at once. So let's see what our mission is, to produce a C. And there's actually only one game in town here. And then, yeah, so that's G of something, and then we want is sitting right there. Here's a tip, actually. Sometimes it's good to play this game where it's tricky. I'd quite like to highlight things, but I can't. Well, we could raise
maybe you can highlight them on the screen, and I try to replicate that.
Well, no, it's multiple. Yeah. So okay, the game I want to play is it coming or going? So if we're supposed to be delivering a D, we're going to need something that gives us a D. So every time you move from output to input, you swap polarity. This is what I want to play is a kind of an even versus odd game. This is, given these two things, make a D, but one of the things that we've been given makes Ds. And this is the thing that makes Cs. This thing that makes D wants Cs, but it gives us A's and B's. So this is sort of kind of way of refining just your perception of the game that you're playing. So back when we were, before we did G of A, when we had our A and our B, right, we wanted a C. And we were trying to, my previous criterion, is there anything that talks about C? And there are two things which talk about C, but which of them is going to be any good to us? G makes Cs, F eats Cs. So which one are we going to pick? So yeah, so it's useful to be able to ask, to read through a type with these nested arrows and pay attention to how many times you flip-flop between input and output to see whether something's leaving or arriving. So here, yeah, the right thing to do is to use G, and then fortunately we've been given A. Okay.
So in terms of statements, yes, you're saying if I can prove A, then G is the implication A implies C. Yes. And then if I can, then F is the implication that I've got A, B, and C. And that gives me
yes. Yeah, but what's going on is a sort of big higher order jigsaw puzzle. And the important thing is to tell the difference between the lugs that stick out and the holes where the lugs go. So this is 1 to D. This is D sticks out. This is needs a needs a C. So this is a hole for a C. Here a C sticks out. So we can see that, so here there's a useless B that doesn't go anywhere, but that's okay. Useless is fine. Every time there's something that's going to demand something, there's a supply for it. So that's what so I'm just suggesting that in terms, if you ever kind of see yourself with a sort of screen full of this stuff and it's a big jigsaw puzzle and you're trying to figure out how to put it together, instead of just thinking which is talking about it, about the stuff that I'm interested in, you should also ask, is it talking about it in a positive, I give you a supply of this way? Or is it talking about it in a, I would need to be given one of these sort of way? Yes, oh, that's absolutely crucial. It's one of those things that the sort of tradition in the mathematics literature is to present proofs in an up the garden path style, where you know some stuff and then you deduce some more stuff, and then you deduce some more stuff from that, and eventually you go, actually, this thing I've figured out now, that's really interesting. Whereas the game that we play is we say, give us one of these, at which point you're allowed to look at the problem in order to figure out what move to make. And that's a significant simplification of the game that we're playing. It's going to turn out to be actually really important. Okay, so let's fill that back in.
Sorry, Rob, could we replace the B there with underscore?
Yes, you can. And Agda will be perfectly happy with that.
But if we got rid of that, we'd
yeah. Yeah, we should also perhaps see what happens if we go back to the original X4 problem and just do Control C, Control A. Because, propositional logic, it's a solved problem. Okay, it doesn't pick very nice names. Yeah, right. So GA. Yes. So this business of, oh, I need one of these. Do I have anything that makes one of those? What does that mean I need? There's an algorithm that solves that problem, and it's baked into the auto machinery.
Also, active do partial functions, right? Which we could put an X for as just giving a G, and then given the second half, given just an average expression of the right.
Yeah.
I can't talk about right now.
Yeah. So you can shuffle these at the F and the G left of the equal sign. Yeah. Yes. So.
And then we just get rid of the F on both sides as well.
No. That's not achievable. In that you have to explain that you're going to use F. You can get rid of last thing on the left, last thing on the right, but not first.
So of course, applying F to that thing.
Yeah.
So that's space. So the first space is saying it's the first argument, second space is applying it to it. But if you curry it, that's the same thing.
Right. The point is that it's already curried.
Okay.
Yeah.
So that was the situation where we can throw away the argument.
Because you're applying the function, the function to the same argument.
Yeah.
Thank you. Sorry about that.
Yes. Okay. I'll do the next one and then you can have the fun one. Right. So I guess we need to explore the definition. So we've seen that we represent and using records with two fields. Now we're looking at a boring true proposition wherever it's hiding. Data.unit.base, I suppose. Agda.builtin.unit, goodness me. Aha! Right. Okay. So when you declare a record, you are allowed to give by convenience a constructor, but the important part of a record declaration is saying what fields the record has. And here is the classic case of the dog that doesn't bark. The unit type, this symbol is pronounced top, or, well, it's the symbol is pronounced top, the type is called unit. It's written \top, I suppose.
Yes.
And it is the record type with no fields. Okay, so remember that to construct a record, you have to give a value for all of the fields. And if there are no fields, giving a value for all of the fields is very easy. You know, it's already done. None left. This is an excellent question. Right, then, but it's not the question we're getting to next. Next question is, what use is it to know a record in this record type? What use is it to know a record? Well, what's useful in a record is that you can get access to its fields. So knowing a value in this type is completely bloody useless, but at least they're extremely easy to manufacture. So that's why this represents trivial propositions. They're extremely easy to prove, but they don't do you any good.
Sorry, the record, is that a record type?
So this is declaring a record type.
It's a record type, not a record.
Yes.
It's of a record type.
Yes.
Okay, and how many records are there in the record type?
Yes. So there are no fields. So how many records are there? That's the point of this thing, is that for the most part, records are equal if they are equal component-wise. So it is the case that this is a genuine unit type. There is exactly one value in this record type. The one named by this constructor, but you can also write it as record, the keyword record, and then an empty set of curly braces. So Agda knows they're all equal, which is great. Okay, so right, so and that is indeed the reason why we use records when we can, rather than whenever you've got a free choice between using a record and using data, you use a record, because Agda knows that records are equal component-wise, and it doesn't do any such thing with data.
So records are a simplification of data.
Yes, they're a very special case. They're a special notion of data where there's only one way to build things, and that's to give values for all the fields. And then they are equal component-wise, which is a more generous way of just testing whether things are equal. Okay, so here we've introduced we tried to show that anything implies true, and all sorts of things we can do. We can give TT directly. That's okay. Or if we ask Agda to figure it out, it figures out that it's TT. Even more excitingly, we can write an underscore and note the background does not turn the yellow of suspicion. So when we say underscore on the right-hand side, we're saying, I don't care what this is because you already know what this is. And when you say to Agda, you already know what this record is, Agda will think, well, I can figure out what this record is if I can figure out what all the fields are. Oh yeah, I can figure out what all the fields are because there aren't any. So it's happy. In fact, you can even delete this B and leave an underscore. Because when you say to Agda, you know what this function is, it goes, well, okay, I'll lambda the argument, the input, and see if I know what the output is. Oh, now I need to figure out what this record is, so I need to know what the fields are. Oh, I can, because it hasn't got any fields. So I'm done. So you can just write, boring here. I mean, this is basically just saying, this is boring. Yes, because functions are equal if they are equal on arbitrary inputs. Right, now, that's important. One has subtle distinction here. Functions are considered equal if you feed in one arbitrary input, the same arbitrary input to both. That's to say, you invent a new variable of the input type, you feed in the variable, and we see if the same thing comes out. That's not the same as testing them on all the individual values that that input can have.
Can you give an example where you is that the same finite?
So okay, we're into murky territory here. So Agda, systems like this always have a variety of competing notions of when things are equal, or some things are more equal than others in the Orwellian sense. There has to be a notion of equality where which the type checker uses for compatibility, right? You want to feed a function its argument. The argument better have a type that's equal to the input type of the function. So there has to be a notion of equal for that purpose. And we can't have a type checking algorithm unless that notion of equal is a bit stupid. In the sense that it can't do magic. It can't solve philosophical problems in order to figure out whether a function and its input are compatible. So there's always going to be some limitations. So when Agda is comparing functions for equality, it will do one test, feeding in a fresh variable that stands for anything, and see if the same thing comes out. Exactly. Yes. So for example, actually a very straightforward example is if you define not on the Booleans, and then you want to test whether not. So that not on the Boolean is going to be like we do a case analysis to see whether we got true or false, and then whichever one we get in, we give the other one out. Right. So in particular, if you feed in just a fresh Boolean variable to not, it will do this. It will get stuck because it can't see whether the variable is true or false. So not of a variable is going to get stuck. Whereas if you apply the identity function to a variable, you'll get your variable back. So that's an example of two functions which are equal on every possible input value, but which Agda is too stupid to see are equal. At the level of comparing things that show up in types. So that's a gnarly situation that we're going to get into.
And I guess we'll be talking way more about equality, hopefully on Thursday.
It's bound to happen.
Yeah.
Okay.
So that is happening soon enough.
So, so we've seen what the representation of true is. It's something. It's the record with no fields. It's extremely easy to make a proof of true. In fact, it's so easy that Agda does it itself, and it is completely useless to be handed a proof of true. Okay, so let's move on to false, which is much more entertaining.
And that's the definition of false, which is just an empty type. So we're listing all possible constructors to construct false, and there are none of them. And that might be a bit suspicious. How's that remotely useful? So we get a type that we cannot produce a value out of, a value in. But the usefulness comes from the other point of view. Now, if we're given a value of type false, we can do a lot of stuff. In fact, we can do everything, because we can ask Agda to pattern match on that value, and Agda would be so happy that it wouldn't require us to do anything more. So if we have a value of type false here, so let's say that this is a function taking a value of type false into any other type. So if we have our value and we ask Agda to pattern match on that, mind you that we know that it is impossible to produce a value of type false. So now when we pattern match, Agda will give us that this is an absurd situation, and it wouldn't require us to finish our definition. In particular, we will be able to produce a value of any type whatsoever.